So after running tests for missing data and replacing the MCAR data, and also identifying and windowing the univariate outliers, as well as removing the multivariate or inconsistent responses, it's then necessary to check for normality within your dataset. So univariate normality applies to the error term or the residuals. It is therefore expected that there is a normal distribution of error or random error between the independent variable and a dependent variable. So the normality assumption is especially important for smaller sample sizes, after which the central limit theorem presupposes a normal distribution of error. The normality assumption is important as it affects type 1 error. A non-normal distribution of error is less likely to produce a significant result. In order to test normality, you can assess the Shapiro-Wilk test, ensuring that you test this for each group separately, as each individual group will have a different distribution of normality. And we'll see what that looks like now. So here we have the data set that we last ended up with when we were checking for multivariate outliers. And so we have our multivariate outlier up here. And so we'll just run on this data set, still looking for univariate normality. So what we want to do is we want to split up the groups again, so to identify normal distribution of error across the groups. So we're going to select cases, and this was already in here from previously, so we just, if condition is satisfied, and it's already got group equals 0 there, so, and as before, it will cross off all of the ones that are not group 0. From there, we can go to Analyze, Explore, or Descriptive Statistics, Explore, and we want our factor, so group, and our two dependent variables as well. And we want to go to plots and normality tests with normality plus plots with tests, and continue, and OK. Now what we have here is we have the Shapiro-Wilk test. So this will show us the univariate normality of each of the dependent variables separately. Our null hypothesis is that there is a normal distribution of error within each dependent variable across the group. If it is significant, then we reject our null hypothesis, thereby assuming that there is not a normal distribution of error. And as we can see in errors, this dependent variable, there is not a normal distribution of error within this dependent variable. And from our data set, we have yet to replace the 18 here because this is a multivariate and also a univariate outlier. So if we're going to Windsor this and change that to 6, presuming, of course, that it's not a data entry error. And if we run the normality test again, so explore, and this would all be here from previously, and OK. If we go down, we'll see the Shapiro-Wilk test again. And as we can see here, that univariate outlier was actually making the distribution non-normal. So that's essentially why it's incredibly important to check for univariate outliers first, because if you do have some within the data set, then it's going to be non-normal. Now the Shapiro-Wilk test is utilized for univariate normality or testing for univariate normality. But when you have more than one dependent variable, you need to check for multivariate normality. However, this is a really tricky assumption to actually assess because there's no direct test within SPSS. And it's typically assumed if the Shapiro-Wilk test is non-significant for each of the dependent variables across each of the groups, you can basically assume there is multivariate normality. If you want an exact test for this, it depends on how good you are with the SPS syntax, because there is a test, Mardina's test, or Small's omnibus test of multivariate normality, and if you're quite adventurous with SPS syntax, DiCarlo actually has created a syntax for these tests themselves. But it's basically up to you whether or not you want to adventure that far into syntax. So subsequent to testing for univariate and multivariate normality, further assumptions that you want to be checking later on, the assumption of non-multicollinearity, whereby variables should not be highly correlated with each other so as to deem one of the variables redundant, and also homeostasticity, whereby variables should have a common covariance of scores.